Is it started? All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. The weekend's about to start. Just pray that you'd be glorified in what we do this day, Lord. In your name I pray. Amen. So, we're now on to lecture 11, which is on a big, glorious, and interesting new idea. Well, completely new for many of you, mostly new for some of you, depending on whether or not you had my linear. I do talk about the concept of a coset when I teach linear algebra, but not everybody does. Some people are smarter than I am. Let's see here. So, we've actually already been working with cosets all along. The truth of the matter is Z mod n, right? The things that we're working with in there are really cosets. So we'd like to generalize that idea a little bit. So let me just get right into it. Definition. Let G be a group with H a subset of G, H not equal to the empty set. Then define AH, which is A times H, such that H is an H. And also defined, so let's see here. HA such that H is an H. All right. So this is the so-called left H coset. Left H coset with representative A, and this is the right H coset with representative A. So I'm assuming a multiplicative group, right? If you had a group with a star operation, perhaps you'd say A star H or H star A for the right coset, right? If you had an additive group, we'd talk about additive cosets. In fact, that's what happened in linear if you had it with me. We talked about additive cosets like this or like this, right? But for an abelian group, it's pretty easy to see that left and right cosets are the same, right? Like if that addition is commutative, then A plus H is equal to H plus A. It's the same set of points. If you just look at it, the definition. Now, I've made this definition for a non-empty subset, but primarily we're interested in the case that H is a subgroup. And when H is a subgroup of G, it's very interesting. There's many very nice properties for the coset. So we need to work through those right now. All right, we get through it, get to it. It's my proposition 3.12. And so here we're going to now I'm saying H is a subgroup. All right, subgroup. And let's suppose that A and B are elements of the group. Then we have a bunch of interesting features for the coset. First of all, A is in AH. Second of all, AH is equal to H if and only if A is an element of H. Point number 3, we have equality of cosets. AH is equal to BH. Oh, I'm sorry, I can't count. Either, I'll get to it eventually here, either the cosets are equal or they're disjoint. Point number 4, AH equals to BH if and only if A inverse B is an element of H. I'm taking a moment to pause there because I have, in past years, accidentally transcribed the inverse on the wrong thing, and it has led to 10 minutes of much suffering. So it's important to get the inverse on the right one there, otherwise, es no bueno. Point 5, the order of AH is equal to the order of BH. Here I mean order. In other words, count the number of things in there, yeah? So like the order of this class. I think the order is 21. I don't count. I'm in a class of my own. What's that? Or I have no class, depending on what day and how you ask me. You could say I'm classless. I wouldn't disagree. I mean, I'm chewing and lecturing at the same time right now. All right, if and only if. Undoubtedly, that's offending someone on the internet. AH is equal to HA if and only if H is equal to AH A inverse, where I define AH A inverse to be that. The natural thing, okay? I mean, you conjugate by A. It wouldn't be wrong to say that this is the forward image of the conjugation map by A. Oh, maybe it would. What was my conjugation map? Did I put the G or the inner automorphisms? Did I say phi sub G? Did it have the G inverse on the left or the right, the formula? Do you remember? Phi G of X was GX G inverse, or was it G inverse XG? Okay, then we're good. I mean, this is the image under the inner automorphism phi A, if you want to write it that way. And then finally, 7. AH is a subgroup of G if and only if A is an element of H. Goodness, I don't remember using 7, like ever. It's in my notes, though. Great. All right. So page 83 of my notes. Yep.
So just to clarify, in the definition of a coset, is A implied to be an element of G?
Oh, yeah. Yeah. I'm sorry. Yes. My apologies. Would you guys, well, I'm not going to let us prove. I will give you examples soon enough. What have I done? No. Oh, page 83 of my notes has the proof of all of these things. Okay, fine. I'll give you one example. You talked me into it. Example, if we look at H equal to NZ, so the multiples of n multiples of Z, where n is greater than or equal to 2, pick your favorite n, right? In this case, A plus NZ is exactly this guy. So that's why I say it's an example of cosets. Right? I haven't emphasized much that n times z is a subgroup of the integers, but it is. Right? It's actually just kind of a strange quirk of fate that I haven't given that as an example yet. I mean, usually I give that as an example. It's kind of an important example, right? All right, so how would we prove any of these things? These are all statements about equality of sets, right? So how do you prove statements about equality of sets? Yeah, usually you prove that they're subsets of each other, right? Or you can sometimes just explicitly show that the condition is met. Like 1 is easy, right? So to prove number 1, we say, well, A times E is equal to A is an element of AH, since E is an element of H, right? I've included the well because it's kind of like, I mean, I could put duh. I mean, this is just obvious, right? A is in AH. But, you know, for the purpose of test 2, please don't give me duh as a proof. It won't go well. All right, so let's do number 2. Assume AH is equal to H. Also, I do not appreciate arguments of the form, I can't prove this, so I'm going to prove something else. Like, that's not a valid method of argument. I mean, I appreciate that you're trying to show me you know something, which is, you know, you're adhering to like a larger point of what I said, which was to convince me you know things, which is good. But still. Just saying. That should not have resonated with so many of you. All right. So if we assume AH is equal to H, what's that mean? Oh, then, well, A is an element of AH by 1, thus A is an element of H since you know AH is equal to H in this part. I mean, okay, great. I mean, yes, the forward implication holds. I think the reverse implication is a little bit more interesting, maybe. I don't know. We'll find out. Suppose A is an element of H, right? Oh yeah, now this is the part that's actually going to, now we have to show AH is equal to H, right? Notice well, let's see here, consider H and H. I'm trying to show that H, what I'm trying to show right now, guys, is that AH is equal to H. So at the moment I picked an element of H. I want to show that it's also where? My goal is to show that this is also in AH, right? So how can I rewrite H into something in AH? How about this? Note, H is equal to A inverse H, right? And A inverse H is an element of H. Since what? Since A and H are in H, right? Thus, H equals to A times A inverse H is an element of AH. Thus, H is a subset of AH. Because I just picked an arbitrary element H in H, right? And I've showed that it's also in AH. It was crucial that A was in the subgroup. Otherwise, I couldn't have argued that A inverse times H was in the subgroup, right? Yep.
Are you saying that H is a subgroup or a subset?
Subgroup. I said it was a subset in the definition, but here I've said more. In the proposition, purpose of the proposition, subgroup, purpose of the definition, I allow it to be something more.
So like right there, that's a subgroup?
Yeah, that's supposed to be subgroup, thank you. Well, no, this is, excuse me, that's subset. You got me, processing. I'll catch up with your question eventually. My mouth just went before my mind. Sorry about that. These things will happen. All right, conversely, let X be an element of AH, right? Then there exists H1 in H such that what? X is equal to AH1. And what am I trying to do? I mean, what does that say? Where is A? A is in the subgroup. Where is H1? It's in the subgroup. So by closure of multiplication of subgroup, this is an element. Right? I mean, because we've shown it's a product of things in the subgroup. Remember, I'm still assuming that A is an element of H throughout both of these. So, thus AH is a subset of H, and so we find H is equal to AH, yeah? Follows. There's proof of 2. Let's look at 3. Debating. I know we don't have time to prove all of them. The question is which ones are most interesting to see proved. 3 is probably worthwhile. So the claim is either AH is equal to BH or their intersection is empty, right? So what should we do? We should suppose that AH intersect BH is not empty, right? And then what do we need to show in order to prove 3? They're equal, right? That suffices to prove 3, does it not? You see what I say? See why that's logical? All right, so if that's non-empty, there exists X in the intersection, yeah? If X is in the intersection, that means that X is in both. But what's that mean? That means that there exists an H1 and there exists an H2. In the subgroup H, such that what? Such that X is equal to AH1, and that's also equal to BH2. So you can see two different things from this, right? You could see that A is equal to B, H2, H1 inverse. And you can also see that B is equal to A, H1, H2 inverse. And I think either of those give us license to rewrite the coset of A, coset represented by A, as the coset represented by B. Let's see if that's true. Let's write it down. So if we look at AH, what is that by definition? That is A, H, right? Such that what? Such that H is an element of H. And what is A equal to? We got a B, H1, H2 inverse, H, such that H is an H. Notice that here H1 and H2 are fixed by the previous step in the logic, but H is the unadorned H is a variable. So we can prove that this is equal to prove this is equal to BH, what do we need to do? What should we show to make a convincing argument that this is BH? We should make a convincing argument that as we allow H to vary over the group, the subgroup rather, that H1, H2 inverse H can take on anything in the subgroup, right? So how do you make such an argument? How about this? Pick, I mean, I'm not disagreeing with you, but I'm saying let's try to be careful. So let's pick, I mean, we need yet another letter. Pick, if we pick, I need another letter. What's that? What? W? Okay, whatever. Pick W and H. Can we rewrite then? I'm trying to think of. I mean, what I want to. I'm missing my words here, guys. What I want to say is that this is the same as B times W, such that W is an H. But I don't think that's quite convincing. I mean, how can I prove that? I want to prove that H. Well, here's what I want to prove. I want to prove that the mapping, specifically that the mapping F going from H to H by F of H equals to H1, H2 inverse H is onto. So if I say W equals to H1, H2 inverse H, then what does that make H equal to? Looks like H2, H1 inverse W. Yeah.
Could you say that H1, H2 inverse is an element of H, and then use like property number 2? So since that's an element of H, then that's just equal to H.
Yes, I think there's another way to argue this. Yeah. So class time is precious, so I don't want to belabor this longer. To make this exactly precise, I'm not quite satisfied yet, but you know, a good almost argument is when you're multiplying. This can be made precise anyway. This has to go over all possible values of the subgroup because H is arbitrary, and you can. You can take the thing you want to hit and just multiply it by the inverse of this element. They cancel out, and then you get the thing you want to hit in the subgroup. So this ranges over everything, which is what I'm arguing over here. The point is that this is equal to BW, which W is free, so that's BH again. Now, what Stephen's saying is not wrong, and that's the other probably way I should have done it. If I wasn't grading your test before class, I might have been better prepared. Sorry. My apologies. So I think if I am to understand Stephen's argument correctly, he's saying, well, you've got AH, but you could also rate A as, what was it?
H1, H2 inverse times H.
Right, so BH2, H1 inverse times H, and that is a subset of what? Or it's equal. Subset or equal? Oh, equal by 2. So we just use 2. Oh, so embarrassing. B H2 H by 2, right? Which is equal to, because H1 is in H, right? So we're letting H1 play the role A did in 2. And then we can suck in the H2 there. And again by 2, which gives us that they're equal. All right. Yeah, that's how I should have done it. Stephen, why didn't you say this 5 minutes ago? That's what I want to know.
I mean, wow.
Oh, okay. Well, that's good, though. That's good. All right, so 4 is actually important if and only if. So can you guys see why AH is equal to BH if and only if A inverse B is an H? Can we prove that? Let's see here. Suppose AH equals to BH, right? Then A is an element of BH, right? Which then says what? There exists H in H such that what? A is equal to B H inverse. Hence, what am I trying to find? A inverse B. So like solve that. Hence, E is equal to, this is just what I see right now. It's not the best, guys. A inverse B H inverse, which then implies that H is equal to A inverse B, right? Which is an element of H. You might not have needed the middle step. I just, in my current level of non-thinking, need the middle step, okay? The other direction, if A inverse B is an element of H, then there exists H in H such that what? A inverse B is equal to H. Thus, B is equal to HA. B is equal to Ha. But perhaps I could have used part of 1, 2, or 3 to prove this. I'm ignoring them at the moment, just trying to prove it directly, yeah. Not the greatest practice, but it's what I'm doing. So what am I trying to do? I'm trying to show AH equals to BH. Oh, what's this show? Actually, I am going to use 3. Yep.
Should it be B is equal to AH?
Oh, yeah, yeah. And that's better because that's an element of AH. Thus, AH intersect BH is not equal to the empty set, as it at least includes B, right? Because B is in BH. We know that from part duh. So by 3, they're equal. So to test equality of cosets, we need to check if the representative inverse times the other representative is in the subgroup, right? This is how to check if cosets are equal. In the additive notation, that just looks like, you know, basically minus A plus B, or we would have written it B minus A before, right? We check whether Zn cosets are equal by seeing if their difference is in the subgroup, which means it's a multiple of n. This is not new, but now for multiplicative groups, yeah. And all right, so to prove 5, you just need a bijection. We need a bijection between here and here. So what's a bijection between AH? So you guys, give me a map. Psi, I want to map psi go from AH to BH. Can you guys tell me the map? Psi of, you know, here's a typical element. AH, what do you map it to? What's that? BH? Yeah, that's the map. Of course, you could, I think you could express the same a little bit differently. You could say that this is equal to B A inverse X, and that would be the way to write it without assuming the inputs AH. I think that's the same map. It just converts the representative from A to over to B. Anyway, can you tell me what the inverse of that map is? See, writing it this way, that's just left multiplication by BA inverse, right? So it becomes clear that the inverse of the map is just, left multiplication by the inverse, right? In other words, psi inverse of y will just be AB inverse y. And if I can write down the inverse, it's a bijection. And if I can write down a bijection, they're in one-to-one correspondence, which is to say they got the same size. All right? I think that's enough on this proposition. Let's go on. I'll come back to the examples, actually. The thing I want to do before I get the projector out is to prove Lagrange's theorem. So what's Lagrange's theorem? Simply says this: if G is a finite group, all right, and we have a subgroup of G, then the order of the subgroup divides the order of the group. Moreover, the number of distinct left or right cosets, where was it, is the order of G divided by the order of H. And we have notation for the number of left or right cosets. It's called the index. The index of H in G is by definition, it's the number of left cosets, so it's G colon H like this. And so what we're saying is that index, the number of left cosets in the group, it's equal to the order of the group divided by the order of the subgroup, just like that. This is Lagrange's theorem. The proof is really, really fun. So you look at G, right? It's a finite group. It's got a subgroup of H, right? So that means that this is H unioned with, say, A1H, unioned with A2H, union with, let's say, well, I mean, this is, if you like, this is EH, right? Let me make that 2, 3, K, H. Now, how do I know that, how do I know everything in the group is in some left coset? Give me an element of the group. Pick any element. G. What left coset is G in? Or let's do it. A is an element of the group. What left coset is A in? Like, okay, very good. Let's see. Okay, sorry. So I had to reindex the question. So clearly everything is covered by some left coset, right? Furthermore, by 3, they're disjoint, right? So the union of the distinct left cosets, so what I'm saying is here, AIH intersect AJH is empty for I not equal to j, okay? I can do that by 3. But what else do I know? By 5, what is the size of each one of these cosets? How many things are there in each one of these cosets? As many things as in the subgroup, right? So count. The order of G is equal to the order of H plus the order of H plus the order of H plus da-da-da-da plus the order of H, because these are all the same as this, which is H, in terms of their size by part 5. That is equal to K times H, which shows you, right, order of H, which shows you that the order of H divides the order of G, right? And so that's the proof. The rest is just notation. See, because K is equal to the order of G over H, and it also is, by definition, the index. It's the number of distinct left cosets of H and G. We knew this. Okay, so this is an improvement on what we knew for cyclic groups Y. Yeah, this is for abelian, non-abelian. It has to be finite, right? But let's see. We did not know before. We did not know that the order of a subgroup had to divide the order of the group for a non-abelian group. Like that, for a non-cyclic group, this is not something we knew before. We knew that this was true for cyclic groups. We know more for cyclic groups, in fact, right? We know that if we have a divisor of the order of the group, there exists a subgroup of that order, right? And we know how to generate it. And we even know how many different ways there are to generate it, right? This theorem does not say that if you have a non-abelian group of order 18, or a non-cyclic group of order 18, that there has to be a subgroup of order 9. It says that if there is a subgroup, its choices are order 1, 2, 9, or 18, the whole thing. That doesn't mean that there has to be a subgroup, just that there could be. And it's not always the case that there is a subgroup of the order allowed by Lagrange's theorem. The fact that that always happens for cyclic group is part of what makes cyclic groups so special. Now you might ask me, well, can you give me an example of a non-cyclic group for which there is a order which divides the order of the group, but there doesn't appear a subgroup of that order? And no, not off the top of my head. I don't remember. But examples like this do exist, and we'll find one, right? We'll find one here. But I'll probably forget to make a point of it when it happens. So consider this. If A is an element of G, a finite group, right? Then the order of A has to divide the order of the group. This is a corollary to Lagrange's theorem that we did not yet have. What's the proof? The proof is simply this. The cyclic subgroup generated by A is a subgroup of G. Hence, the order of the cyclic subgroup of A must divide the order of G. And of course, the order of the cyclic subgroup is the order of A. Cool thing, this is true even for non-cyclic groups. This is new. Another corollary that we can extract here from Lagrange's theorem, if I can find it. I keep losing. I've hid it in plain sight over here. The other corollary I should mention, a group of prime order is cyclic, right? If the order of G is equal to P, then G cyclic. We can now prove that. pretty easily with Lagrange's theorem, right? If A is an element of G and A is not equal to E, then this, right, is a subgroup of G. And the order of A equals to this divides P. P being prime, your choices are either 1 or P. But 1 is out because we assumed A is not the identity. Therefore, the order of A must be P, which makes A a generator for the whole group. Pretty neat, huh? Another corollary is that A to the group power is the identity. Again, I'm in a finite group, all right? In a finite group, if we raise any element of the finite group to the order of the group, we must get the identity. How would you prove this? Oh, well, anyway, time it is a-flying. Let me make sure we see the examples today before we run out of time here. So I really like Lagrange's theorem because it gives I think, a convincing and satisfying answer for why you care about cosets, right? The fact that it allows you to prove Lagrange's theorem so beautifully is reason enough, I think, to look at cosets. But there's so much more, because what we're going to see next lecture is that we can use cosets to form yet another associated group to a given group, possibly. If we have the right kind of subgroup, we can form what's called a factor group. Now, in order for that to make sense, we have to have a certain condition on the subgroup called normality. But if we have a normal subgroup, then we can construct a factor group, which is yet again a group. It has a relation to the given group, but it's not the same. We'll get to that next time, of course. That's not for today. What I want to do with the rest of the 5 to 3 minutes that I have today is to show you the examples. Come on. I'm eventually going to get back to our... What lecture are we on? 11. All right. So, example, I think this is my first example. Oh, no, I have some simpler ones. This is the proof. Here we go. We'll start out with an easy example. There you go. So here in Z... Am I going to have to go get Dr. Scambortis? I'll do it. I will find somebody who to come in here and talk to you guys about cell phones. I can't do it because I answer mine in class sometimes. But anyway, so Z6 is this. H is a subgroup of order 2, and check it out. 1, 2, 3 subgroups. 3 cosets, 3 distinct cosets. The index is 3. Lagrange's theorem. 3 times 2 is 6. Yay. Here in Z100, we have the subgroup of order 5 generated by 20. Or 60, I guess. And as you can see, well, partly see, there are in fact 20 distinct cosets, ranging from the subgroup to 1 to all the way to 19. Again, you can see Lagrange's theorem in action. There are 20 cosets because 100 divided by 5 equals to 20. 20 distinct left cosets. The index of H is 20. You can also see cosets in linear algebra. In particular, if you look at the solution set to AX equal to B, we learned that the solution has the form particular plus homogeneous, where the homogeneous solves this. That is a subspace, which is to say it's a subgroup of Rn with respect in the sense of Rn being an additive group under vector addition. And so actually we're looking at left cosets of the null space of A. That's a way to look at, in fact, the solution set is a coset. Finding the particular solution gives you a representative. You can also look at a subspace of a vector space. P plus W is a coset of W. You can think of it geometrically as a parallel translate of the subspace. You could do the same thing for lines, if you like. I talk about that in here, some different geometric interpretations of cosets. No, I will not click on the Wikipedia article link. It's very tempting. It's got really cool looking foliations, which are more general than this. We can talk about SLN is a subgroup. The special linear group is a subgroup of GLN, right? We could look at left cosets. We could look at right cosets. I prove here, actually, that the left and right cosets are equal. So GSLN is equal to SLNG by this argument here. That, by the way, means that SLN is one of those normal subgroups that we'll learn about next lecture. Lagrange's theorem we proved. I proved that corollary for you. I proved that corollary for you. I punted on the proof of the third corollary. Here's the proof. By the first corollary, we know that there exists a k for which g is equal to k times order of a. So if you take a and you raise it to the order of g, that's like raising a to the order of k times a, which is a to the order of a to the k. But by the definition of order, that's e. So there you go. Now, this is a very greedy thing to do. In practice, in typical groups, you can the order of an element will typically be less than the order of the group. It's just the order of the group will for sure make the thing go to the identity. Now this right here is easy to go through now that we have all of this technology. So we can actually classify groups up to order 7. Because let's think about it. Up to order 7, we got 1, 2, 3, 4, 5, 6, 7. Which one of those are prime? 2, 3, 5, 7, right? So those are cyclic by the corollary to Lagrange's theorem. Order 1 is the trivial group, right? Order 2 is Z2. Order 3 is Z3 essentially. Order 5 is Z5 essentially. Order 7 is Z7 essentially. If you look at groups of order 4, we have seen that you can either have a cyclic group of order 4, right? If you don't have a cyclic group of order 4, that means what? You must have, if you think about it has to be the Klein 4 group, because if you think about it, it has to have more than one element of order 2, right? The identity is unique. The only possible divisors of 4 are 1, 2, and 4. If it's not cyclic, it doesn't have an element of order 4. By process of elimination, we must have more than one element of order 2. Which is why you have to write, in fact, you have to have 3 elements of order 2. Because you can't have an element of order 4 and you can only have one identity. So everything except for the identity has to be an element of order 2, which forces you to write this Cayley table. And the things in red you're forced on just by the fact that each row and each column can only have one of each letter each place. You just think through it. You're forced to write that. Once you write that, the associativity of that is given because this and that are the same pattern. Consequently, yes, it's the Klein 4 group. And then order 6 is a little bit trickier. Order 6, you can only have elements of order 1, 2, or 3. So either you have a cyclic group of order 6, right? Or if you have not a cyclic group, you have to have either elements of order what? 2 or 3. So you have to have 5 elements which either have order 2 or 3 if the group is not cyclic. And if you sort through the details of that, it forces you to say that it's S3. I have made this a homework in past years. Be glad I did not assign you that homework. It was unpleasant. The end result of it is that there are two groups up to isomorphism of order 6, either the cyclic group of order 6 or S6, and that's it. So here you go. This is a complete list of up to isomorphism, the groups up to order 7. Order 8, it starts to get interesting. On the test, you might have noticed that Q8 and D8 are not isomorphic because Q8 has 6 elements actually of order 4, whereas D8 does not. D8 has, what does it have? Am I saying D? I meant D what? D4. Yeah, D4 has how many elements of order 4? 2, right? A and A cubed. So they're not isomorphic. You might ask how many other groups of order 8 there are. Well, there's Z8, so there's at least 3 groups of order 8 up that are not isomorphic. I'm not sure what the total list is. I seem to remember 5, but I could be wrong. But anyway, sorry I started late and ended late, but now we're done. So you can hit it. Your